So, welcome to the Quantum Summit 2024. Integration of quantum compute into an HPC data center, or maybe in some data center at least. So, this is a huge topic. And as Claudia Bechstein was in the opening celebration talking that we're going to interact with the audience, a question to you. Who's part of some of these integration projects? Is there any member of some integration project, quantum compute into a data center? I identified one. And I will cite from this project. So let's go into deep dive for this integration. It's a huge challenge. So there's only one expert here in the room. Let's see what we can have for challenges and how to tackle these challenges. So we are in the data center business. Rosenberger Hochfrequenztechnik is with 15,000 employees doing connectivity, and especially for the optical solutions, we are with 800 employees doing the passive data infrastructure for data centers. And that's why it's a big challenge and a big endeavor to integrate the quantum compute systems into existing data centers, and especially for high-performance data centers. Rosenberger is providing components as well for cryogenic systems, for Oxford Instruments and so on. So this is part of our work as well, being a manufacturer for quantum computing systems. Yeah, the challenges are ahead and the samples as well. So I will shed some light on existing running projects on the schedule. There's a Forschungszentrum Jülich ongoing integration project, adding 2 quantum modules, one from Electron, which is an ion trap system, and a superconducting system from IQM. And there's a experience with IQM. I will show this. But first, I heard Robert Habeck maybe is not approaching this location. If not, this is Robert Habeck, so if you see him. He was just visiting Siegen Electron and get to know the system, and he wants to know the economic dimension of all this. So Robert Habeck is very interested in this kind of systems, and he looked at this ion trap. And you see a photo of 33 ions in a row. It's taken from the camera. It's taken from this vacuum chamber chip. You see the chip at the top of the vacuum chamber, and this photo was taken from this chip from this vacuum chamber. The other part, IQM, successful integration already done in Munich. This is a sample we will show that HPC data centers we will need to concentrate on just not any HPC data center, but just on one sample and 2 types of quantum compute. And I prepared some other stuff which I was not able to follow up, so we just skipped this for 20 minutes, so this is enough for 20 minutes. There are so much scientific papers out there, and these scientific papers, I'm really happy that they were published, because in these scientific papers you find the only technical details about the integration. If you go to a vendor and say, hey, I want to download the tech spec, give me the manual, you would have no answer. So concentration, I'm a senior project manager doing the integration project, and that's why we concentrate not on so much technical integration, but just the approach, how to do it, how to approach this, and what is the recommendation out of this approach as a project from the project management point of view. So we found, as we are starting with consultancy for this kind of large projects, we found more or less 3 challenges. The one is the common language, because the quantum tech guys, the quanties, so to say, are not able to talk to the classical IT management guys, because it's completely different naming. And availability of tech specs, I just mentioned this, and availability of skills, of course. So you need the qualified, certified personnel, I don't know. So as we have only one member of an integration project in this room, so you see there's maybe a skill shortage. And how do we tackle this skills shortage? So now let's just see the sample projects which were successful. There was one project, it's not an HPC data center, but it's a co-location data center in Japan. There was a successful integration from Oxford Quantum Circuits. They did it in November 23, and it was successfully integrated. It was the first, more or less the first, for industrial use implemented quantum system in a classical data center. That's why this is really good to have this role model, this sample. And then in the middle, I'm glad to have her here, Laura Schulz, part of this project. I will cite from the scientific paper as well, because there are some technical details in this paper you had published. So this is a successful integration at the LRZ in Garching. The IQM machine was integrated there. And then this, I just in the beginning outlined Forschungszentrum Jülich, the ongoing implementation, integrating this electron ion trap system and an IQM system for the Jupyter supercomputer in Jülich. I had found some parallels to my last speech at German Data Center Conference, because I was dealing with the topic AI solutions, and for these AI solutions, I was investigating in the typical reference architecture for data centers in general, and that's why at the opening, Sarah Elsayer in the Bad Vilbel some weeks ago, she was going into the data center history and said, the first data center in Germany opened in 1963 in Darmstadt. Right? No. The first data center in Germany opened in Garching, 1962. And these were the first large computer system implemented in Germany, integrated. And so our perspective is as well to learn from this past, to learn, to see what are the best practices. We have an experience of decades dealing with this kind of large computer systems. This was IBM. Telefunken was a competitive, but they decided for several reasons to integrate the IBM system. So this was really interesting. Just to give you a small number, a figure, 56 megabyte hardware cost for the system was $185,500 at that time, which is more or less $1.5 million today for 56 megabyte capacity. So what we can learn from all of these projects, there's a reference architecture for AI data centers in the meantime available, for instance, with Schneider Electric. And there are differences in the future of data centers, if it's a use for high-performance computing, if it's a use for AI, if it's a use for a classical co-location data center, for instance, and then integration of the quantum module is a challenge, because you need to adopt this for every type of data center. And that's why it's really needed and required to have a closer look at this kind of reference architecture. And what is the difference? The typical AI data center is entirely different. It has got liquid cooling up to 40, 50, 60, 70 kilowatt per rack. And you have large supplies. So you see the space for the systems in a classical data center is more or less 70%. The space for the systems in the AI data center is just around about 40 or 45%, because the supplies of you need. And that's why it's entirely different if you want to integrate a quantum module in which kind of data center, HPC, AI, classical data center. So you need different approaches, and you need really to go into a deep dive for the requirements. That's why old school doesn't work in hybrid data center. Common language, I just told the example was at Electron in Siegen. I was discussing with Christoph Wunderlich, the mastermind of Electron, and I said, how you want to plan to connect the qubit instances? And he said, instances? Okay. I said, okay, he's not understanding instance in a classical system convention. So I said, okay, let's connect the quantum nodes. quantum nodes, he didn't get it. So we need really to come to a common language to talk about quantum technology, quantum computers, HPC, AI data centers, and this is just under development. Yeah. So that's why we need to rely on conferences, on workshops, on Congress to see where are the information, where are the guys, where you can expect you need the technical specification, where to get it, yeah, to have a proper approach to start this kind of integration project. And it was really good to see Heike Riel from IBM, maybe who was in her speech yesterday. Okay, there was mentioned a project, integration project in Japan. So this is the integration of the Falcon IBM quantum chip into a supercomputing center Fugaku. So this will be really a good sample to see that we can develop much more experience, best practices to use in the next project, the next project, next project. So it's really good to see all of these technical workshops and conferences going on. This is where we need to rely on as long as we do not have the possibility to just download the tech specs. The next challenge is the availability of skills. So we have a skills shortage on the one hand. There are master programs. You see the global proportions where master programs in quantum technology are available. So where you get your PhDs for your project, and this is currently the global situation. It's not so bad for European Union. So you see European Union, we have a lot of quantum talents. We can expect that we are able to staff this kind of challenging projects by our own purposes, by our own resources. So this is really good to see we have a chance to do this in Europe. And now just a sample to get this technical details, the technical paper. Laura Schulz is an author of this as well. So there I found some of the technical details for the computer systems to control the quantum computer. And this is what you need when you plan the settlement for the data center. And the challenges are, for instance, calibration. So you need to tackle the calibration, and if you calibrate the system, you cannot use it. So you have a period of calibration, use, and this is in a sequence of, I don't know, Laura, maybe you can tell something about the sequence. Calibration takes how long, and then you can use it again? Depends. Okay, maybe it accelerates. Yeah. Thank you. So that's why we need to have really full respect of these successful projects done already, because they did a great job doing this. This is where we have a pioneer work we can rely on this experience, and this we can need for the next integration, large integration project, to have a controllable timescale, have a controllable budget, and see what we have for possibilities to integrate this. Learning from the past, dealing with large computer systems, classical IBM mainframe, implementing in a data center, it's kind of a standalone system. So you see, it's a large machine, it's a standalone system. Just guess, when you implement a large IBM mainframe system, it's a standalone system, how many of these systems you need to implement in a data center in a typical environment? Just guess, how many? It's a standalone system. How many do you need? Maybe there's some mirroring. 2? No, you need 3. Because you need 3, because in case of an error, of a problem, of a disconnect, you get in the risk of a split brain situation. And that's why you have a so-called coupling facility, which is the third mainframe, just doing some logging. And in case of a split of an issue, then this third machine can reinstate the mirroring between the failover productive system. And this is a principle we need to figure out if this is what we need for quantum modules as well. So this will all be investigated and done in the future to see in which kind of installation, in which kind of arrangement, which kind of module or sequence and parallelization we need to implement the systems. So learn from the past is a good thing, and go with this kind of project into the future, tackle the challenges, develop a common language, tackle the tech spec availability problem, and get the right people, the educated, skilled, certified people on board at the right time. So to summarize, we have this from the approach point of view divided in the integration sphere, calibration sphere, which is a technical issue more or less, the maintenance of the system while bringing up the project, and the maintenance in daily operation. And then, of course, the programming. We've seen a lot of samples for programming as well in other presentations. So that's why you need to rely on partners. We, for instance, talked to Fraunhofer Focus. They developed this Eclipse CRISP programming environment, which is really a good thing to get into a better state to set up the system control, to have the programming in place with the coverage of the right requirements at the right time and so on. And you need some kind of a middleware solution of a training and education and customizing solution, which is, for instance, provided by Q-Control, successfully in the past. So go into this kind of projects not alone. Take partners. This is the message. And just to see one small sample in what this partnership can bring, just in software programming. Have you ever, I guess there's some representative from the CRISP program as well here? Sebastian, Raphael, okay. So thank you. Yeah, we discussed this at Tuesday. Yeah, Tuesday. If this would be some part of the solution to get the kind of a software part, the middleware part for integration of the quantum module with the HPC data center in control. So this maybe is one part where we have really a good and strong platform for developing the software needed for this integration. So thank you for giving this insights. And that's it. From the project management point of view, kind of lessons learned we will have in the future with the upcoming project, especially Forschungszentrum Jülich, will be really a good situation with IQM Electron. There will be a lot of experience then with this large Jupyter computer system, and this is what we need for future integration projects. So thank you very much. Maybe you have some questions. Thank you.
Thank you.